So this is the we do section of infinite limits and their pals. So as we go through these first problems, the first three we're looking at rational functions, which means we're going to be looking at the highest degree exponent to in each the numerator and the denominator to figure out what the limit is. So as we approach positive infinity, our highest degree exponent in both the numerator and the denominator is 3. So that means our limit is going to be the ratio of the coefficients on the highest degree terms. So that only happens when the highest degree term is the same in the numerator and the denominator. In the next problem we're looking at as we approach negative infinity of 5x cubed and x squared are our highest degree terms. Since the larger degree term, the cubed, is in the numerator, that means we're going to be approaching either positive infinity or negative infinity. So for this, we have to look at the terms now and think about, well, if I plug in a huge negative, cubed, like just imagine we're doing bigger and bigger negatives here, and a huge negative squared, we're going to have a negative divided by a positive. So that would be a negative. So we're going to approach a negative infinity with this guy. But we'd also say it does not exist. The next one, we've got a higher degree in our denominator than in our numerator. So that means it approaches 0. These three problems are just a matter of remembering your rules. So we need to make sure we know those going forward. Next, we're talking about the log function. So we should remember what that function looks like. Looks like this. It's got a vertical asymptote of the y-axis. So if we're approaching 0 from the right, that would mean we're going down here. And we go down forever, so that would be negative infinity, or it does not exist. As we go to infinity with log, we're going off this way. X is going to infinity. This guy just goes up forever, so that would be positive infinity. Does not exist. For secant, all right, I'm going to encourage us to think about what that graph looks like. So secant is 1 over cosine. So if you remember, we've got our cosine graph. Oof, this is tough. All right, I should do this in a different color. Our secant graph has asymptotes where cosine is 0, and then looks like parabolas. So as we approach pi over 2 from the left, we go up forever. It's infinity. It does not exist. As we approach from the right, it's going to be that parabola is going to be down here on that one. So it's going to be negative infinity. Does not exist. Lastly, we've got a rational function, which factors. You don't need to know how to find the removable discontinuity, but I'm going to just do it out now. So we've got x equals -2 is that canceled term. Y equals 5 divided by -2 plus 5. 5/3. Okay. So we've got a hole at -2 5/3. So that's 1.6. About here. All right. Our graph shifts left 5, so we've got a vertical asymptote at -5. And a horizontal asymptote of the x-axis. So just a rough sketch of our graph. looks like this. So as we approach -5 from the left, our graph is going down forever, so negative infinity. As we approach -5 from the right, we're going up forever, so positive infinity. As we approach -5 overall, we do not exist, right? And we've got that same thing for each of these. And then as we approach negative infinity, so go all the way off to the right, we get closer and closer to 0. And that, you'd notice, is consistent with our rational function rule because the highest degree term is squared, or 2, and that's in the denominator, so it'd be 0. Same thing for this one. Our rational function rule applies, but we can also see it from our graph as we go off to the right, it approaches 0. That's all, folks. Go ahead and try the I do problems.